India, home of 1.3 billion people, is a confluence of religions, traditions and customs. A thriving global center of technology and the world's largest democracy. As one of the oldest civilizations in the world with a rich cultural heritage and diversity in the world, India is proud to assume the presidency of G20. As the country blooms into a new era, we look to another poignant symbol for humanity to emerge victorious from its challenges. Lotus, the national flower of India, representing our culture, history, and heritage. A poignant symbol for humanity to emerge victorious from its challenges. And the inspiration for India's G20 logo design. The design, rendered in saffron, white, green and blue, is drawn from the national flag of India. The 7 petals in the logo signify the 7 seas and the coming together of 7 continents at G20 2023. Sitting above the lotus is a representation of the earth, reflecting India's pro-planet family. From this 23, Vasudhaiva Kutumbakam. A theme that brings while being in harmony with nature. G20 India 2023. One Earth, one family, one future.
With me is my co-commentator Shrivika Swankar giving the commentary in Hindi. We are joining you from the Mission Control Center, 3,900 kilogram.
New position yet? Working on it.
चंद्रमा की सतह पर लैंडर का सुरक्षित लैंड करना और अंत में रोवर का चंद्रमा की सतह पर विचरण करके तात्विक तथा रासायनिक विश्लेषण कर वैज्ञानिक आंकड़े जुटाना।
On your TV screen, Honorable Minister of State for Science and Technology and Prime Minister's Office, Dr. Jitendra Singh.
आज के मुख्य अतिथि के रूप में यहाँ उपस्थित हैं विज्ञान और प्रौद्योगिकी राज्य मंत्री माननीय डॉक्टर जितेंद्र सिंह,
We are about 31 minutes from the scheduled launch time. You're watching this live from the Mission Control Center. Apart from Doordarshan, you can also watch the launch event on ISRO website, YouTube, Facebook and Twitter.
सुदृढ़ चंद्रयान 3 L110 चरण है जो कि तरल नोदक पर आधारित चरण है और इसके ऊपर की ओर 28 टन के क्रायोजेनिक ईंधन वाले C20 इंजन का प्रयोग करते हुए C25 चरण है जो कि भारत का सबसे बड़ा क्रायोजेनिक इंजन है। इसे इसरो के लिक्विड प्रोपल्शन सिस्टम सेंटर IPRC द्वारा विकसित किया गया है।
And the day of launch, wind biasing data is fed during the countdown to the onboard computers to enable most suitable steering of the launch vehicle through atmosphere. Up next, we will watch a curtain raiser video on this mission.
Number 465 request PDS to confirm supply of CH2 to cryogenic.
Moon. This familiar object in the night sky has inspired the imagination of astronomers and ordinary people alike. From time immemorial, humans have marveled at the beauty of the moon, used it to count time and navigate the high seas. In modern times, Moon, the only natural satellite of the Earth, has acquired added importance due to the belief that Moon is the key to our understanding of the evolution of the solar system in general and Earth in particular. Besides, Moon's precious resources and low gravity have further endeared it to humans. India, a major spacefaring nation, has conducted a detailed exploration of the Moon through its Chandrayaan program. The country has sent 2 robotic spacecraft to orbit the Moon and to take a repeated look at its surface. Chandrayaan-1 demonstrated India's ability to reach the surface of the Moon at a place and time of its choice. And with it, India became the 4th country to reach the surface of the Moon in November 2008. Besides, Chandrayaan-1's conclusive was praised as a path-breaking discovery. The follow-on mission, Chandrayaan3, had an orbiter, a lander called Vikram, and a rover named Pragya. In the past 4 years, the orbiter has repeatedly observed the lunar surface and even today is working satisfactorily. Now, 3,900 kilograms Chandrayaan3 spacecraft is being sent to the moon with the objective of making yet another focused attempt to slowly land on the lunar surface and to explore it with the help of a rover. Following the spacecraft launched by India's most capable rocket, LVM-3, the Chandrayaan-3 lander carrying a rover within it will be carried into an orbit around the moon by the propulsion module. A little later, the lander will separate from that module and will attempt to make a soft landing in the south polar region of the moon. This region is of intense interest as it has many permanently shadowed craters which could contain water ice and precious minerals. Chandrayaan-3 lander has 4 scientific instruments or payloads, of which one will study the moonquakes, while the other one studies as to how the surface of the moon allows heat to flow through it. The third one will study the plasma environment near the moon's surface. And the fourth instrument will enable scientists to measure the distance between the Earth and Moon very accurately. The 2 instruments on the rover help us study the composition of the moon's surface using X-rays and laser respectively. While the lander and rover will be in direct contact with each other. The propulsion module circling the moon will observe the light coming from Earth, the only planet which we know which is definitely teeming with life. This observation will help in understanding the nature of distant planets circling stars other than the Sun. As Chandrayaan-3 undergoes important tests and gears up for launch, thousands of ISRO scientists, including those who will launch it, control it, and receive the precious scientific information from it using giant dish antennas, are readying themselves for the challenging tasks ahead. In the past, their dedication and skill have enabled India to earn praise from across the world and made it proud. Let us wish them well in this great endeavor called Chandrayaan-3.
आपके सामने हैं इसरो के अध्यक्ष श्री एस सोमनाथ। अभी अभी आपने देखा एक संक्षिप्त वीडियो जिसमें एनिमेशन की मदद से इस पूरे मिशन की यात्रा को बताया गया है। इस मिशन
30 seconds. Real-time programs activated. Minus 20 seconds.
L1 10 VS पे भी open.
Minus 20 seconds. Minus 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Plus 5 seconds.
Lift off normal. P1
Here
tracking.
we have a majestic liftoff of LVM-3 M4 rocket carrying India's prestigious Chandrayaan-3 spacecraft.
P2 tracking.
प्रज्वलन और सफलतापूर्ण उत्थापन LVM-3 M4 रॉकेट का। यह भीमकाय रॉकेट आसमान को चीरते हुए अपनी भयानक दहाड़ से चारों ओर कंपन उत्पन्न कर रहा है, जिसे हम यहाँ महसूस कर सकते हैं, और यही दहाड़ है जो वैज्ञानिकों को रोमांचित करती है। LVM-3 के उत्थापन के साथ ही हमारे अंतरिक्ष यान चंद्रयान-3 की चंद्रमा की यात्रा प्रारंभ हो चुकी है।
As the rocket is soaring through the clear skies, every second moving closer to the accomplishment of the most important milestone in its mission to moon. Every Indian witnessing the launch live is content with the feeling of watching history in the making.
चंद्रमा की सतह पर अपना छाप छोड़ने के लिए चंद्रयान 3 अपने मिशन को पूरा करने निकल चुका है। वर्तमान में दोनों S-200 स्टेप-ऑन बूस्टर सामान निष्पादन करते हुए अपनी निर्दिष्ट कक्षा की ओर बढ़ रहे हैं।
The S-200 motors thrusting simultaneously, generating a peak thrust of close to 6,000 kilonewtons in vacuum. They are made of HTPB-based solid propellant. 204.5 tons in each strap-on. Close to 2 tons of propellant being burnt each second.
S-200 स्टेप-ऑन बूस्टर्स का कुल प्रज्वलन काल 126 सेकंड का है और अभी घोषणा की गई L110 स्टेज का भी प्रज्वलन शुरू हो चुका है।
Apart from the strap-ons, the core stage has also commenced its operation. This stage, based on combination
200 stages are separated.
of hyperbolic Earth storable liquid propellants UH-25 and N2O4. Now the S-200s have been separated.
घटनाक्रम के अनुसार इस यान से S-200 स्टेप-ऑन बूस्टर्स को सफलतापूर्वक पृथक कर दिया गया है। यह काम सेपरेशन मोटर्स की मदद से किया जाता है। इसके बाद L110 तरल नोदक पर आधारित और विकास इंजन के साथ यह चरण सामान्य निष्पादन करता हुआ अपनी उद्दिष्ट कक्षा की ओर बढ़ रहा है। अभियान क्लोज लूप गाइडेंस के अंतर्गत है।
L110 stage performance normal.
The trajectory of launch vehicle is closely following the prediction.
Payload fairing separated.
जी हाँ, पेलोड फेयरिंग को पृथक कर दिया गया है यान से, क्योंकि यान अब 114.8 किलोमीटर की ऊंचाई प्राप्त कर चुका है। इस चरण का कुल प्रज्वलन काल 200 सेकेंड होता है और इस दौरान यह करीब 1600 किलो न्यूटन का प्रणोद उत्पन्न करता है।
We are 220 seconds past the launch time. Current altitude is 135 kilometers. In the 200 seconds of its operation, the L110 stage carries the rocket up to 175.5 kilometers altitude and imparts a relative velocity of 4.18 kilometers per second, that is 250 kilometers every minute.
Do you have the courage to make 8 lakhs a month, which is 1 crore a year? See,
L110 stage performance normal.
पर तृतीय चरण क्रायोजेनिक इंजन को शट ऑफ कर दिया जाएगा। और उचित अभिवृद्धि प्राप्त कर चंद्रयान 3 को यान से पृथक कर दिया जाएगा। चंद्रयान 3 को LV
Cryo stage thrust cut off. Satellite injection condition is achieved.
अभी पुष्टि की गई चंद्रयान 3 को प्रमोशन की कक्षा प्राप्त कर ली गई है।
Chandrayaan 3 satellite separated.
चंद्रयान 3 को सफलतापूर्वक अंतक्षेपित कर दिया गया है एलिप्टिकल पार्किंग ऑर्बिट पर।
Chandrayaan 3 has attained a major milestone successfully.
Chandrayaan 3 mission accomplished. Handing over to mission director.
Mission control, mission director. The LVM-3 M4 Chandrayaan mission accomplished its precise satellite injection conditions. LVM-3 M4 mission is successful. Thank you.
The launch has also added a feather in the cap of LVM-3 rocket. You can watch the jubilant congratulatory gestures of ISRO scientists in the Mission Control Center.
जी हाँ, चंद्रयान को सफलतापूर्वक अंतक्षेपित कर दिया गया है, लेकिन चंद्रयान 3 की यात्रा अभी जारी है। अब इस मिशन के बारे में हम अध्यक्ष महोदय से सुनेंगे और हम आपसे आज्ञा लेते हैं।
We sign out.
नमस्कार।
Up next is address by Secretary DOS, Chairman ISRO.
Once again, good evening to everybody. We are celebrating the mission moon success of India, the space success of India, and every day, every evening, we are coming to you in this platform with some lectures from our legendary scientists of ISRO, PRL, DST. And today also we are going to celebrate the mission Chandrayaan3, the success story of ISRO and Indian scientists, along with the promotion of our upcoming event, that is 5th year of India International Sarabhai Student Scientist Award, which will be started with a Google form based e-quiz in a preliminary round from 1st January 2024, and step by step there will be 5 rounds on astro experiments, on virtual simulator using, through which you also do similar things what ISRO scientists do in Chandrayaan or Mangalyaan. You can prepare a rocket or launch vehicle, and you can launch it, and after launching you can orbit the vehicle, and making trajectory you have to land on the surface of Moon, Mars or Venus. So after these assignments we will evaluate once again, and we will select 5 students who will be conferred the award, India International Sarabhai Student Scientist Award. This year also we have conferred this award, which award is e-certificates, and this year we are very much grateful to the scientists of ISRO and NASA both, because on behalf of NASA and on behalf of ISRO, 2 scientists signed the certificate and we have conferred that one. So congratulations. We are inviting all the students to get in touch with us when we are this time promoting our program event along with the success of mission Chandrayaan. So moving forward, today we have one legendary scientist with us. He is none other than Ashok Ambastha. Sir is very much a legendary person in the Indian experiments of solar system and solar astrophysics. Sir is, I am just briefing about sir. Sir is now attached with PRL, being a professor and scientist under PRL, and especially attached with the Udaipur Observatory, Solar Observatory, which is situated at Rajasthan, Udaipur, and those are already got superannuated, but sir is dedicated scientist who is serving PRL and observatory till date, being professor and as a solar astrophysics expert. Professor Ashok Ambastha, former senior professor, Udaipur Solar Observatory Physics Research Laboratory, which is very much known as PRL, and the mother institute of ISRO even, which is started and established by legendary scientist Dr. Vikram Sarabhai at Ahmedabad. Professor Ashok Ambastha obtained his MSc in 1974 from Pandit Ravi Shankar Shukla University, Raipur. After that, he joined PRL Physics Research Laboratory, Ahmedabad, where he received his doctoral degree in 1981. In 1983, he joined Udaipur Solar Observatory, which is also known as USO of PRL, and contributed to the formulation and consolidation of USOs, that is Udaipur Solar Observatory scientific programs. Sir has superannuating as senior professor in 2014. Sir is also till date joining with dedicated to this institute for various research purpose also. He worked as at the NASA Marshall Space Flight Center, USA during 1992 to 1994 as an NRC Senior Resident Research Associate. He served as a counselor 1998 to 2001 and the Secretary 2004 to 2006 of Astronomical Society of India, which is known as ASI. Member of COSPER, URIS, SCO, STEP Committee of INSA, New Delhi during 2008 to 2012, and in the editorial board of Journal of Astrophysics and Astronomy during 2010 to 2016. Professor Ambastha has led total solar eclipse expeditions to many countries for studies of the structure and polarization of solar corona. He has guided several students of MSc and PhD degree and various research programs also, and has published over 100 research papers in international scientific journals. He edited 4 books proceedings and has authored Physics of Invisible Sun, Instrumentation, Observation and Inference, which has been published by Tyler and Francis Group, CRC Press, USA, published in 2020. So such a legendary professor, an astrophysicist who have so much knowledge, depth knowledge about the sun. And as we know, ISRO's next mission is AdityaL1, to observe, to investigate, to critical analysis of for sun, and which will be the another milestone for ISRO and Indian science heritage also. So I think there is no need of such introduction. better we can listen him, which is the main motto of our program also. So, sir, I think over to you, sir, and welcome you too.
Okay, thank you so much, Anjan. Can you hear me? Can you hear me? Hello. Yeah, am I audible?
Yes, sir,
Anjan?
we are hearing you, sir.
Yes. Is this audible?
Yes, sir, yes, sir, yes, sir.
Okay. So thank you so much, Anjan, for your introduction, and also for inviting me to give a talk on the platform which you are managing so creditably. So I think I would like to make my presentation here. If I see the presentation, yeah, so I found here the presentation and share screen, and I take the share screen and entire screen, select this. So, okay, so now you should be able to see my slides here. Is this clear to you? I mean, the first slide.
Yes, sir, very much clear, sir. You can
Okay,
start.
so yeah, so I'll be talking about India's quest of observing the sun. Basically, I work at the observatory, solar observatory in Udaipur, which is called the Udaipur Solar Observatory, which is a unit of Physical Research Laboratory, Ahmedabad, which is dedicated to observing the sun from the ground. And there are I'll basically give in this slide the outline of my talk. So first I will very briefly talk about Vikram Sarabhai, about which already you have been talking a lot, and essentially to the foundation of Physical Research Laboratory by Professor Vikram Sarabhai, and discuss about PRL's role in the space program, and then go over to current scientific activities of PRL, and then I will switch to solar physics, which is done from Udaipur Solar Observatory, essentially the ground-based observations. But there are some limitations. So there are requirements of observing the sun from the ground and also from space, as we will see. There are several solar activities and energetic phenomena which can be best seen from space in high energy radiation. So one has to go to space for observing those. So I'll go over to that. So essentially, I'll talk about these activities and their influences in space and also on the planetary environment, including the environment of our Earth. So this actually constitutes the space weather, which has become a very important subject of late. In between, I will also talk about various types of solar instruments which are dedicated to a measurement of various parameters related to the sun, which are operational at USO, and then talk at the at the later part about AdityaL1 mission, which is basically the first dedicated Indian space mission for observing the sun. Of course, the first Indian astronomy satellite was AstroSat, which was launched few years earlier. But this one, which is expected to be launched somewhere in August end or September first half, will be dedicated to the observations of the sun from space. So essentially, this gives a brief idea about the talk which I am going to deliver today. First, let us talk very briefly about the architect of Indian space program, Professor Vikram Ambalal Sarabhai, who was born in August 12. Very few days back, we celebrated 104th birth anniversary of Professor Sarabhai. So he was born in 1919. And at early age of around 52 years, he passed away in December 31, 1971. In fact, he was born in a very affluent business family in Ahmedabad, and after his preliminary education in Ahmedabad, uh, essentially in Gujarat College, he left for England for higher studies in physics in 1937, and he received undergraduate degree of Cambridge University in 1940. But around that time, World War II broke out, and therefore he had to return back to India. And there, after returning, he joined Sir C.V. Raman at Indian Institute of Science as a research scholar in Bangalore. And there he started working on cosmic rays and built equipment for his measurements from various places, including Kashmir. Uh, After the war was over, the Second World War was over, he returned back to Cambridge in 1945 in order to complete his studies there, and he was awarded the PhD degree by the Cambridge University in 1947. So after that, he decided to return back to India, and he founded Physical Research Laboratory in 1947, essentially first as a modest lab at his own residence in Shahi Bagh, Ahmedabad. And again, this was dedicated to research on cosmic rays. PRL was formally established on November 11, 1947, in MG Science College, Ahmedabad. So essentially, he moved his laboratory from his residence to a few rooms in MG Science College, and there PRL formally started in 1947. So it is PRL is almost as old as the India, from the independence from British, and in MG Science College, his initial focus in the early stage of PRL was on cosmic rays and upper atmosphere, in which he was very much interested. Later on, research in theoretical physics and radio physics were later added on. And Professor K.R. Ramanathan, who was one of the bright students, who worked on Raman effect with Professor C.V. Raman. So after his superannuation as the Director General of India Meteorological Department, Professor Ramanathan joined PRL as its first director, although it was founded by Vikram Sarabhai. But Ramanathan was kind enough to take the directorship of PRL in the first, after its establishment. Sarabhai was later the director of PRL from 1965 to 1971 till he passed away. And in fact, he also served as chairman of Atomic Energy Commission during 1966 to till his death. In fact, he died in November 1971. So it is, after that, in 1972, it was taken over by Professor M.G.K. Menon. To implement the space program, Sarabhai took some major steps during 1961 to 1966, and he expanded PRL Ahmedabad by making it the headquarters for space activities of India. PRL contributed significantly in manpower and scientific formulations of early developments in space research. Therefore, appropriately, PRL is also called the cradle of Indian space research, and Sarabhai is fondly remembered as the father of Indian space program. In the left, we have some old pictures from PRL archives, where Jawaharlal Nehru, the first Prime Minister of India, is inaugurating the new campus of PRL in 1954, which moved away, from MG College, We had a new campus then, where we have the present campus. Uh, Also seen our Ramnathan here, K.R. Ramnathan, and of course he is Vikram Sarabhai with Jawaharlal Nehru. And this is another picture later on, where I think this is from the Silver Jubilee of PRL, uh, where Mrs. Indira Gandhi is seen with Dr. U.R. Rao and Dr. Devendra Lal, who was the director of PRL after Sarabhai, and he was a very dedicated physicist involved in lunar sample analysis, which first samples came to India from Soviet and American spacecrafts. The PRL got those early samples, and there was a lab in PRL which was established by Devendra Lal, who whose group was basically uh, dedicated to the analysis of lunar sample. So PRL has a very early history of association with the moon. Very briefly, we'll talk about the evolution of Indian space program. Here already, I think you must have got several talks from ISRO's engineers and scientists. So I'll be very briefly talking about, just to recapitulate, that after the first satellite launched, Sputnik was launched by Soviets, and later on followed by NASA in there after the Soviets. Uh, in the early stages itself, Dr. Sarabhai understood the importance of space researches, and he established Indian National Committee for Space Research, or in COSPAR, which is predecessor to ISRO. And he convinced the first Prime Minister, Pandit Jawaharlal Nehru, to start this first under the Department of Atomic Energy in somewhere in 1962. So that was the kind of a beginning. And in COSPAR set up Thumbar Equatorial Rocket Launching Station called TERLS in Thiruvananthapuram. That time it was called as Trivandrum. There is a small village near Trivandrum where TERLS was founded for essentially for upper atmospheric research by using small rockets. Space Science and Technology Center at Thumba was set up for creating fabrication, testing, and other auxiliary facilities. Experimental satellite communication Earth station was established later on at Ahmedabad, which has now grown as Space Application Center, which develops lots of payloads uh, for the programs, various programs of ISRO. INCOSPAR was reconstituted on 15th August 1969, and ISRO was created under Department of Atomic Energy to conduct space research and application. Sarabhai picked a team to realize an Indian satellite launch vehicle called SLV, which has grown into PSLV and nowadays, of course, as GSLV, and so on. With the sudden death of Homi Bhabha in an air crash, Sarabhai was appointed chairman Atomic Energy Commission in May 1966. So essentially, he worked for a short time, but he made a huge amount of contributions to Indian space program, to ISRO. So in fact, after Sarabhai, he served till 30th December 1971, when he was in Trivandrum to review the SLV design, and unfortunately he died there at the early age of 52 years due to cardiac arrest at the same night. Afterwards, several of his students, notably Dr. APJ Abdul Kalam, Dr. U.R. Rao, Dr. K. Kasturirangan, most of whom had been associated with PRL as engineers and technicians and scientists, students basically, So they pursued Sarabhai's dream further and made what ISRO is today. So here, in fact, this early rocket engineers, a team of early rocket engineers are seen with a small rocket here, and Dr. APJ Abdul Kalam is discussing with Sarabhai here, and you can see the young Professor Ur Rao. So that is about a very brief introduction about the ISRO and the development of a space program. That is not my topic for today. So I'll be moving over to PRL, its scientific activities. In fact, PRL has the main campus in Ahmedabad, and this is the front building is the one which was built in the beginning of PRL in 1954, which was inaugurated by Pandit Jawaharlal Nehru. Somewhere at this floor, Dr. Sarabhai's office was located in this front building, and later on, this eight-story building has been added mostly during the time of Professor Devendra Lal, where most of the divisions of PRL are located, and these divisions are basically astronomy and astrophysics, solar physics, which is mostly at Udaipur, planetary sciences, space and atmospheric sciences. This has been continued from the early stages of PRL. Geosciences, which are basically started with Professor Devendra Lal and then continue. Now, planetary geology and so on have also been covered by this. And theoretical physics, which has nuclear physics, high energy particle physics, and plasma physics. And then apart from that, we also have atomic, molecular, and optical physics at PRL. This gives the PRL's website. These are other campuses of PRL located at other places, including one in Thaltej, which is essentially a suburb of Ahmedabad. So there are some activities of PRL, mostly astronomy, astrophysics, and planetary sciences. They are now located in this campus. While in IR Infrared Observatory, Guru Shikhar, Mount Abu, there is a nighttime observatory. There is a large telescope, and there is a new telescope which has been added up there for observing active galactic nuclei and also searching for exoplanet and so on. And then we have another unit of PRL located in Udaipur, the Udaipur Solar Observatory. One can see here the main office where the laboratories and library, other facilities are located. And right hand side, this picture shows the island observatory where there are different structures which are housing different telescopes dedicated to solar observing from the ground. And one can see that this is in a small island in a large lake called Fateh Sagar in Udaipur. We'll talk about Udaipur Solar Observatory in the next few slides, and also what we observed from Solar Observatory. So one can say this is the bird's eye view of Udaipur Solar Observatory, which was founded by Dr. Arvind Bhatnagar in 1975. In fact, I joined PRL back in July 1975 and did my PhD in 1981, and then I carried out my postdoctoral activity in PRL, and then in 1983 I joined Dr. Bhatnagar as the first scientist to help him formulate the early, scientific programs. In fact, in the early phase, it was not like this. This is the present day solar observatory. In the early time, there was a rolling shade under which a telescope was installed, which was obtained as a gift from Australian and American scientists, which started under a Vedshala Trust. Later on, in 1981, it was taken over by Department of Space for its rapid development because solar observations have very important role in space of related problems. So this observatory was selected after a very extensive site evaluation and site survey program in many places in Gujarat and Rajasthan. In fact, there are various considerations required for professional solar site selection based on clear sky condition and good duty cycle. That means in a year you try to obtain a large number of days which are cloud free, and also the site should be dust free in order to have good seeing conditions. That seeing basically is the quality of observations, where the turbulence because of the atmosphere is minimized. So when your site is located around, surrounding a huge amount of water reservoir, the water helps in reducing the turbulence of air which is in contact with the lake surface. So essentially, the lake and oceans are large water body. These are good for reducing local air turbulence, and they provide better seeing conditions. So one can see the astronomical object with good clarity. So that is one of the major requirement for observation of the sun. There are also high altitude or monsoon sites where the low water vapor and cloudless, dust-free environment allows observation of infrared emissions from the sun, which also provides lots of information. Also, some optical observations are carried out. So there are several such mountain sites where solar observations are being carried out around the world. In USA, in Sacramento Peak Observatory, Kitt Peak National Observatory, in Chile, and in China, and so on. Apart from site, one has to have a careful dome selection. Dome, that means a cover around the telescope, and one has to have a proper building design, which are needed to reduce the local heating and local internal turbulence within the telescope. And because of that, normally a collapsible dome, like this is the building here, there is a collapsible dome which collapses, and the telescope is allowed to observe directly without any enclosure, which doesn't trap the heat inside the dome. There is an older dome here which has a slit, but in this dome, which we used to use earlier, it was found that a lot of heating is generated inside when the sun's energy falls at the floor of the telescope. It starts heating inside, and that goes through the slit here, creating turbulence. So because of that experience, the new telescope which we'll be discussing was built in Udaipur, which has a collapsible dome. So these are some of the considerations which we have for observing the sun. So why it is important to observe the sun? Of course, we have been talking about this. So, see, the sun is the governor of our solar system. It is the source of all forms of energy that sustains the life and also drives the weather and climate on the earth. So that is one very important aspect, that sun is related to us. And Indians have, and many other civilizations have been observing with interest and curiosity the suns over several centuries. In fact, we have several sun temples in India, from Kashmir to Konark and so on. So we used to worship the sun god. But apart from that, in the modern times, the scientists are interested to study the sun because of its importance for life and weather patterns on the earth. It has played a major role in development of mathematics and physics from the time of Galileo, Kepler, Newton, and Einstein. And this is also called as the Rosetta Stone of astronomy. It is also the closest star to us from the Earth, and this is the only star where it is possible to observe and resolve surface features. and the dynamics, the flows, and lots of activities which are related to the structure and dynamics which happen on the sun. So all these things are possible to study directly uh, at the sun because of the proximity. It is only 15 crore kilometers, or in terms of light, minutes, it's only 8.14 light minutes away from Earth. So as a result of that, using modest telescope also it is possible to resolve surface structures and see the details, which I will be showing you. And such observations over seconds to minutes to days and years, we see various manifestations of the sun. We see the quiet structures of the sun at times. Then we see that sun becomes active, and at certain times it becomes explosive. There are giant explosions which take place on the sun, which drive space weather and also affect planetary environment. So as a result of these, it is very important to observe the sun on a continuous manner. Also, the solar interior and exterior atmosphere, outer atmosphere of the sun, they provide a cosmic laboratory, a very giant laboratory to test the atomic physics, nuclear and neutrino physics, high temperature plasma physics, and magnetohydrodynamics, and also to test the general relativity predictions. So these are some of the major importance for observation of the sun. This one gives you very brief general properties of the sun. The angular diameter of the sun, as we see in the sky, is roughly half a degree or 32 arc minute on the average. Of course, our Earth moves around the sun in an elliptical orbit, so at times will be closer, so sun will look little bigger, and at times it will be farther away in the elliptical orbit, so it will look slightly smaller. But this is the roughly average size in terms of arc minutes. 60 arc minutes is 1 degree, so roughly half a degree if you consider horizon to horizon 180 degree. Its distance from Kepler's third law and parallax of Venus, which has been obtained. Of course, nowadays there are several modern technology to obtain the distance. It is 1.5 10 to the power 8 kilometer, which is also defined as 1 astronomical unit. This astronomical unit is usually taken, used for measuring the distances of planets. So the distance between Earth and Sun, average distance, is called 1 astronomical unit, and this is around 8.3 light minutes. Okay, so this is the distance around, in Indian units, it is 15 crore kilometers. And radius of sun, if you consider the angular diameter and the distance, it turns out to roughly 109 times the radius of the Earth, which is 700,000 kilometers. So the size will be, double of that. So radius is 700,000 kilometer. As compared to Earth, you can see this is 109 times the Earth radii. So in fact, on the equator of the sun, you can place 109 Earths, and if you consider the volume of the sun can contain 109 to the power 3. So almost more than a million Earths can be included within the sun's sphere. I mean, sun's size is so big. Its mass turns out to be, from the balance of Earth on Earth, the force due to gravity and centripetal force, as it is moving around, one can use that and obtain the mass of the sun to hold the Earth in the orbit. It turns out to be 333,000 times the mass of the Earth. Is a 2 into 10 to the power 33 grams. Density is 1.4 grams per cc. Effective temperature of I think there is a call, but I'll just leave it. Oh. Yeah, sorry. The effective temperature of the photosphere is around 6,000 degree Kelvin from Wien's displacement law. We can obtain from that from theoretical consideration. From space observations, we get the irradiance or luminosity of the sun, and average magnetic field strength is roughly 1 to 3 Gauss from polarimetry and Zeeman effect. A composition is 74% hydrogen, 24% helium, and 2% others by mass using spectroscopy. Solar rotation is, not solid body. Sun doesn't rotate as a solid body like Earth does. Earth is a solid body, but Sun is gaseous, hot sphere of gases. So it rotates differentially. It is faster in the equator. It takes only 28 days to rotate one complete rotation, while as you go towards the poles, it takes 37 days. So this one can obtain from the motions of sunspot on the solar photosphere and Doppler shift of spectral lines, which we'll be discussing. And from meteorites and from theoretical considerations, the present age turns out to be roughly 4.6 billion years. So this is just a gist of the properties. This shows the anatomy of the sun, basically showing the internal and external atmosphere, internal structure and external atmosphere. One can see this artistic sketch of the solar anatomy, that in 1/4 of the sun, there is a very dense core which is very hot and very dense. Uh, you know, the it is so dense that thermonuclear fusion can take place in the central engine of the sun, which is at 15 million degree temperature, very hot and very dense. As a result of that, there is a PP chain reaction or thermonuclear fusion chain reaction, which continues converting hydrogen into helium and so on. And then the energy which is generated in the core propagates outwards first through radiation and then by convection. So the 0.25 to 0.7 or so of the solar radius is called the radiative zone, where the temperature kind of drops from very high to a modest temperature of around 200,000 degrees or so. And then as it cools down, the convection currents take over to transmit the energy outwards by huge convective currents, which generates the magnetic field inside the sun. And above that, we have the photosphere, which is a yellow kind of layer which you see here. Above photosphere, you have the photosphere is around 6,000 degree Kelvin, as I said earlier. And then above that, the chromosphere, and beyond that is transition region and corona. So this is a very brief introduction about the sun. Each of these can be discussed with a lot of details, and here it shows the profile of height from the photosphere outwards, and here it is showing the temperature. Here it is showing the density in kilograms per meter cube, and one can see the interior is all hidden under the photosphere, but the temperature, one can see that it is dropping in the photosphere to the chromosphere to a temperature minimum level, and then it starts rising, and then beyond the chromosphere, which is around 2,000 kilometers thick layer, photosphere is around 500 kilometer thick skin of the sun, under which the interior is hidden. So you cannot see beneath the photosphere because of the high opacity, and the layers above that are also difficult to observe because of very low densities involved and very low luminosities involved. So photosphere dominates in the uh, brightness, and as a result of that, chromosphere is difficult to see except under certain circumstances we'll be discussing. In the chromosphere and above, the temperature suddenly increases very rapidly to million degrees, while the density falls off very rapidly and then attains a plateau as you go away in space. So this is basically telling you about the welding temperature, silver melting temperature, and so on. And here it is showing the densities, a lab vacuum, which is almost like corona. So corona is so low density that is very close to lab vacuum. So this essentially here describes the parameters which are can be seen from here, how the temperature and density in solar atmosphere varies as you go above the solar photosphere. And the 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 energy which was generated in the core, as I discussed, that it goes through the radiation zone and convection zone, and then finally leaves the photosphere. And photosphere is named as such as a result of the photons which are coming out. But the in the core, high energy gamma rays are produced, and as they travel outwards, they get converted into entire electromagnetic spectrum, and the sun basically emits electromagnetic spectrum which is covering this entire range from gamma rays to shortwave radio wavelengths. And a very small window is the optical window which normally we can see by our eyes. So this is the Webjor, the when you take the white light radiation from the sun, white light emission of the optical emission of the sun, when you use a grating or a prism, one can essentially disperse the light in from the violet to the red, and beyond that infrared and radio, and below that we have ultraviolet, X-ray, and gamma rays, which are high energy emissions. And as you can see that only optical wavelengths can come to the ground, and also longer wavelength like the radio window can also come to the ground. The sun and for that matter other stars and galaxies can be observed in visible band or in radio, but all the high energy photons which are coming from the electromagnetic spectrum of the sun or other stars, they are absorbed by atmospheric layer of the earth at different heights from the ground. Sorry, I'm having a little bit of throat problem. So you can see it, the gamma rays are and X-rays are, absorbed at the heights of around 30 kilometers and above, and similarly, gamma ray can penetrate little more. Similarly, here in the infrared, they are absorbed by the molecules which are present in the atmosphere, atmospheric gases. So as a result of that, infrared also has a problem coming to the ground, and one can use infrared telescope in planes or balloons or in rockets. So these are basically the observations of X-rays, gamma rays, and so on, what one can do from rockets and satellites, while observe the sun and other stars at the ground using optical telescopes and radio telescopes. Okay, so I think that's what you remember, that there are limitations. So I think I put my phone in silent mode, but still there are some phones, they keep coming. I hope still my sound is there, or somebody has any complaint, then one can tell me. Okay. So here we are going to the special features of the sun. This is the photosphere. This image here at the right hand side, which you are seeing, is the image of the photosphere taken from ground, and in this case, actually, this is taken from MDI of a spacebound. But this is something like this you get using a ground-based telescope also. And here you can see some dark spots, which are called sunspots. Okay, and these sunspots are changing with time, different times of the day and year. You will find that they keep changing their shapes. And if you have a very good seeing condition, and if you select a part of the sun around the sunspot, one can actually get pictures like these in the left side, which show that sunspots are highly dynamic, and they are composed of umbra and penumbra, which is the darker part is called the umbra of the sunspot, and fainter part is called the penumbra, which has lots of fibrils which are indicative of the magnetic field lines, connected to the sunspot. And these sunspots are basically lower temperature as compared to the ambient surroundings. And as you go away from the sunspots penumbra, you see a granular structure. These are basically like bubbling of energy which are coming from below the photosphere in the form of small convective cells which are coming up and down all the time. They are forming and getting destroyed within few minutes. So sun is highly dynamic. If you see the clock here, you can see that these are highly dynamic in nature. Okay. So the photosphere shows all these sunspots where the strong magnetic fields are shown as sunspots, and around that also lower magnetic field structures are there. But as a result of the opaque photosphere, we cannot see within the beneath the photosphere is very difficult. We cannot see the solar interior, and therefore the recourse has been taken to mathematical treatment using hydrodynamic equations, and people have tried to make standard solar models where the gravity and thermal pressure are considered as dominant forces for hydrostatic equilibrium. We know that sun is in the state of equilibrium, at least at the right time, at the current times. It is not collapsing or not expanding. And in this standard model, the rotation and magnetic fields of the sun are basically neglected in the first approximation, and equations are solved by computers. And people have tried to build the radial profiles of density, temperature from the core onwards. And only problem is that whether these models are correct, or not. So what are the checks for checking these standard models of the solar interior? So essentially, there are two types of messengers which are which help us in determining the correctness of standard model. One is neutrinos, solar neutrinos, which are produced in the pp chain reaction, where the hydrogen converted into helium, and also neutrinos are generated and gamma rays are generated. And gamma rays which are produced in the solar core, they get converted into the entire electromagnetic spectrum, and then we receive them. But neutrinos are very difficult to detect. There are people who have made neutrino detectors in order to using, these are very weakly interacting particles, fundamental particles, but they still go through some kind of properties, going through certain large tanks which are kept under several kilometers under the ground of the earth, and then using some kind of detector chemicals, people have tried to determine the capture of neutrinos, and from there they have tried to calculate the solar neutrinos, and then that has been now helped to kind of check, apart from the helioseismology, which has provided another tool to study the solar interior using oscillations in the solar photosphere, which has also helped in sorting out the neutrino deficiency problem, and uh, essentially, telling that the solar neutrino which are produced inside the solar core, they get converted into different flavors of neutrinos, and we get certain deficiency, but that has been sorted out now. So it has been found out that most of the standard model, theoretical standard models which have been constructed from hydrodynamic equilibrium equations are more or less correct. So helioseismology is essentially oscillations of the photosphere, which are observed in the photosphere, which have amplitude of few tens of meters per second, very very small amplitudes. So very precise and very accurate instruments are required to detect such oscillations which you see here. These are basically a part of the Doppler grams, which is obtained from the Doppler effect. You are getting bright and dark here. So bright ones are the flow in the photosphere which is coming towards the observer. Dark ones are the which is going away from the observer. So red shifted and blue shifted motions which you are seeing here shows that it is like a sea wave which is happening on the sun, and one can observe for several months in order to very precisely determine the amplitudes and frequencies of these superpositions of millions of different types of modes. Here actually you can see some scans where it is showing up and down related to this picture here, and this is a full disk Dopplergram which has been obtained from Doppler instrument. So helioseismology requires continuous observation in order to obtain accurately the frequency and magnitude, amplitude of these oscillations. And for that, we require to continuously observe, which is not possible from a single station. One has, different possibilities of having continuous observation of the sun, because we know that as Earth rotates in its axis, north-south axis, we have the day and night cycle. So from a single site, we have a day-night cycle. We cannot observe the sun continuously. So one has to have a network of many ground-based observatories in order to have a continuous 24-hour solar coverage. And that kind of thing, one of such international project is called Global Oscillation Network Group, of which one instrument is placed in Udaipur Solar Observatory. You can see this is the place. This is the instruments called GONG instrument, Global Oscillation Network Group, which is a collaborative international project. And the GONG instrument has a small telescope here, which puts the image of the sun inside this cabin, where we make continuous intensity Doppler and magnetic maps every minute. And then there are some other observatories around the world, which you can see here. This is the GONG network, where the observatories, similar observatories as you saw in the previous slide, are being operated in Learmonth in Australia, Udaipur, as I showed you, and El Tigre, there's the Canary Island of Spain, and Cerro Tololo in Chile, and Big Bear in California, and Mauna Loa in Hawaii. So as the sun sets from Learmonth to Udaipur, takes over, and then El Tigre, Cerro Tololo, and so on. So this network is observing the sun from ground using identical instruments, and obtains the Dopplergram, full disk solar Dopplergrams, which are combined merged together. Data from all these 6 sites are merged together, and near continuous data time series is obtained, which is analyzed to obtain uh, the modes of solar oscillation, which has helped in understanding the solar interior. So the solar helioseismology is very similar to Earth seismology, where the volcano eruptions and earthquakes produce the seismic waves which go all around the globe of the Earth. And using various earthquake observatories, people make the models of the Earth's inner structure. In the same manner, using the photospheric oscillations of the sun, helioseismology has been successful in determining the interior structure and also in resolving the problem of solar neutrino deficiency and also in validation of solar standard model. Okay, so near continuous observation from such networks have been several, some other networks are also there, but Gong has been one of the most successful network. Apart from that, continuous observations are also obtained from space, notably from the L1 point in which Aditya is planning to go, from where one can observe the sun nearly continuously. Okay, so that is another option for helioseismology. Okay, so far we had been talking about the photosphere and the science related with the photosphere, mostly helioseismology, the sunspots, and so on. And we saw earlier that the density above the photosphere drops very rapidly in the chromosphere, and similarly, the temperature rises very rapidly. So the layers above the photosphere, the layers of the sun's atmosphere above the photosphere, they remain invisible except during the brief periods of total solar eclipses or by using specially designed solar instruments from ground or space. So let us go over to the other layers. So above the photosphere, you can see the chromosphere. Uh, Traditionally during the solar eclipse, when the bright photosphere is covered by the moon and the bright light of the photo is cut off, then for a very brief period of few seconds to some minutes maximum, it could be around 7 minutes, that one can see the chromosphere and beyond. In the above the chromosphere is the corona, which right now you're not seeing. There's still a lot of light is there. So here you see a red layer, which is not a very regular layer. It is very irregular layer, which is corresponding. The red color is coming because of the red color of hydrogen at 63, 65, 63 angstrom. That is called hydrogen bomber line or H alpha line. And in fact, during the solar eclipses, it was found from flash spectrum of the chromosphere that H alpha line is in the red region of the spectrum, electromagnetic spectrum, which is quite prominent, and it basically is a chromospheric light. So these are all the other lines like helium-1, magnesium, and other lines related to the chromosphere, and H alpha is the most dominant. So if it was realized that if we make some kind of optical filters which are centered in H alpha line at 6563 angstrom or 6562.28 nanometer, then we can block the light coming from elsewhere and also other wavelengths and also from the photosphere. And as a result, the optical filter will only allow the light coming from H alpha line, and using that one can make pictures like this even without solar eclipses. So nowadays, modern days, we have very good optical filters, very narrow band filters centered at this H alpha line, which kind of reject all the light coming from other wavelengths, and one can make pictures like this on a routine basis from ground, because this is optical wavelength. So we can receive this H alpha light on the ground. And at Udaipur, we make such pictures daily, except for monsoon period, right, like now. So such pictures tell you the layer above the chromosphere, and you can see apart from dark sunspots, we also have bright plages, bright areas around the sunspots, which are hotter places, again magnetized places. And you can also see dark ribbon-like structures, So a lot of such structures you see, and you start seeing the importance of magnetic field, which was only seen near the sunspot in the photosphere. Very strong magnetic fields were seen, but here you can see all over that sun is dominant in this layer, in magnetic, as far as the magnetic fields are concerned. So this is the chromosphere, and in fact, using these lines, like the photospheric lines and also chromospheric lines, using Zeeman effect, where in the presence of magnetic fields, the spectral lines are split into a triplet, and from this split, one can obtain the magnetic field. This is the split. Lambda m is the splitting of the spectral line due to magnetic field, which is proportional to the wavelength squared multiplied by b. From atomic physics, we get this expression, okay, and that essentially shows that the split is proportional to lambda square. Larger is the wavelength, you have larger split. So if you go to infrared wavelengths, you will have much bigger split. And also, if you have very strong magnetic field, splitting will be more. But you require very strong magnetic field of the order of 4,500 Gauss or so to produce measurable split in spectral lines. Like if you take example of around 7,000 angstrom or 700 nanometers, which has a Landis G factor of 1, split is only 0.1 angstrom or 0.01 nanometer. So it's very small. Fortunately, this magnetic field produces also polarization in spectral lines. So using polarization instruments, we can infer weaker magnetic field fluxes close to sunspots, and we can make magnetograms like these here. This is the photospheric magnetograms taken at different activity phases of the sun. One can see at times when sun is very quiet or very low activity period of the sun, very few sunspots or sometimes no sunspots are seen. And sunspots are here, for example, you can see that there are the sites of enhanced magnetic fields. And here, this is the time of a maximum activity of the sun, when sun is dominated by a large number of sunspots and large number of magnetized, highly magnetized region on the sun. So these are the kind of activities of the magnetic field variation in the sun based on the activity level of the sun. Okay, we have made a magnetograph facility in Udaipur several years back. This is a full vector magnetograph. All the three components of magnetic field of the solar photosphere is being measured from this instrument, and this was inaugurated somewhere in 2007 in Udaipur. This is Madhavan Nair, the former chairman of ISRO. He was the chairman at that time. So this was the first video magnetograph which became operational in Udaipur, somewhere in 2000. But before this, we also had a longitudinal measurement component magnetograph also, which was part of a thesis of one Dr. Shivu Matthew, who is the head of USO right now. That was done somewhere in 1996 or so, 95 to 96. This is another instrument which is now operational in 2015 onwards, which is the multi-application solar telescope. which has one of the largest aperture solar telescopes in Asia. This is around 50 centimeter aperture, and this is the structure which allows the sunlight to go through the primary, and then it is going to the secondary, and then the sunlight goes to the lower basement, where we have several instruments, back-end instruments, which measure solar parameters and also make the images of the sun at different wavelengths. So this is one major instrument which has become operational in Udaipur Solar Observatory in 2015 onwards. So using such telescopes, we observe various features in the chromosphere. Like here, you can see this ribbon-like structure I showed earlier, also called a filament. These are long ribbons of hydrogen gases, condensed hydrogen gases, which are confined in magnetic field structures, which get destabilized at certain times, and they can erupt. And as they erupt, here you can see the timings here, and here you see that entire filament is erupted, and they create some brightenings, like small flares, and also they go into space, and sometimes they propagate outwards, create lots of disturbance in the space. There are other solar energetic events like solar flares, which take place on the solar disk, which produce a lot of energy in the form of radiation and also high energy particles, which are released. And the energy release happens from flare to small flares to large flare in this range, 10 to the power 28 to 10 to the power 32 Earths, within a few minutes or few hours in a small tube. This is corresponding to this flare here, which is observed from Udaipur, and this is from the space for the same in ultraviolet, extreme ultraviolet, which cannot be observed from the ground. So these are some of the energetic events like eruptive filaments and flares, which we normally on a routine basis one can observe from the ground-based telescopes. As we go above the chromosphere, the temperature rises very rapidly, goes over to roughly 200 degrees, 200 into 2 million degree or so, not 200, to 20,000 to roughly a million degree within a height span of around 500 kilometers. Again, here, this is the transition region, very thin layer, which we cannot, the resolution is, if you consider resolution of around 1 arc second at the distance of the sun is around 600 kilometers. So if you have a resolution of 1 arc second, you cannot resolve the transition region. Also, at the temperature of a million degree or so, few 100,000 to a million degree, most of the elements are fully ionized. Hydrogen is fully ionized, and so H alpha is not observed from the transition region. And transition region mostly emits in ultraviolet and extreme ultraviolet. So one can see these are ionization of different elements. So because the ultraviolet and extreme ultraviolet radiation do not reach the ground, therefore transition region cannot be observed from the ground. It can only be observed from the space. Above the transition region, we have the corona, which is still less dense, is still more than a million times fainter than the photosphere. So you require to block the moon, block the photosphere using the moon's disk, and then one can make integration a large number of different exposures of the corona to produce such images, which show that corona is highly structured, and one can see the dominance of magnetic field in terms of open field lines from the north and south pole of the sun, and related to the active regions on the sun, which are basically the sunspot regions, one can see such closed structures. So such structures can be seen from the ground during eclipses. And apart from that, one can take the coronal spectrum also, like the flash spectrum of the chromosphere. People have taken the flash spectrum of the corona, which shows there are several other lines apart from the chromospheric lines. You see new lines. This is the H alpha line here, which is a chromospheric line. But you can also see some faint signatures, faint emission lines associated with highly ionized iron. This is the iron red line, iron green line. There's a 14, iron 14 is 13 electrons are knocked away from the iron, and so on. So there are some emission lines which are present in the corona, and one can make images of the corona using emission lines, which can be also done from the ground and from the space. So this picture shows such a picture of corona using emission line, using the red and green and yellow line of iron. Again shows you the polar plumes and the structures which we saw in the ground-based white light images. So these are again composite of huge number of images. And since the these lines which you see are basically called the forbidden lines, which require very high temperature of a million degree or several million degree, and very faint low density plasma. Essentially, from the presence of such lines, it has been deduced that corona is very hot, million degree temperature. Although the photosphere is only 6,000 degree temperature, the corona is a million degree at a million degree, which is deduced from the presence of emission lines like these forbidden lines, which are there. So as a result of high temperature, the corona also emits X-rays, and these X-rays cannot come to the ground. And the space era, basically with the beginning of space era in 1974, with the launch of Skylab, people tried to make images of the sun in X-ray from space, and such images were obtained where one can see that above the photosphere, which is represented here with a dark disk here, above that you see the faint emission in X-rays, which is associated with the solar corona. And solar corona on the disk as well as away from the disk can be obtained as compared to emission line corona, which requires the photosphere to be blocked so that the images can be made in emission lines. Here one can see all over the sun, and it also shows certain kind of regions on the sun which are devoid of any X-ray emission. Is a dark region here, which is called a coronal hole, which are locations of open field lines from where one actually sees variety of things happening. And when you observe the such X-ray images and also the occulted, so disks, white light, corona, one can sees from space where the photosphere is occulted, one can see that there are huge plasma clouds propagating away from the sun, which were first discovered in December 71 by coronagraph on board Skylab and OSO 7, it's a NASA satellite, which actually involve huge amount of mass going into space related to the activities, explosive activities on the solar chromosphere and above. They have speeds of around 10 kilometers to more than 2,500 kilometers per second, and kinetic energies are also very large. Again, like flares, these are in terms of joule, but this again like 10 to the power 27 to 10 to the power 32 ergs. Okay, so these are very large. Like flares, they all involve also huge amount of energy, and their rate of occurrences also changes with activity. And here I show you a slide which shows the activity cycles of the sun from minimum to maximum. If you plot the x-axis, this is the year, and y-axis is the sunspot number. If you plot the sunspot numbers with time, it shows the interesting quasi clock-like periodicity, which is roughly 11 years, not exactly 11 years, but it can be on the average called as 11 year. So there is an activity cycle operating on the sun at the rate of at the period of around 11 year. Sun goes through a minimum to maximum. There are some maximum which are very high, like this is modern maximum in 1957 or so, modern maximum. And there are times when there are sun is not very active. There are very prolonged period of time where not many spots, almost none of the sunspots were seen, which is related to modern minimum, and so on. So it shows that sun is active and inactive in different time scales. And here it shows that depending on the phase of activity on the sun can be very bright in X-ray, and also it can become very dark. So from solar maximum to solar minimum, these are pictures taken in X-rays by Yoko telescope, Japanese telescope from space, showing the changing phase of the sun over one 11-year cycle. And above the solar corona, there is a solar wind particle, which is essentially the expanding corona, which is propagating away from the sun in terms of hot electrons, protons, and minor fractions of helium-2 and heavier ions with a mean speed of 4 kilometers per second into space. But there are also slow and fast solar wind streams from 300 to 800 kilometers, depending on from where they are coming, from the coronal holes or from the active regions and so on. And these streams which are going from the sun away into the space, they rotate with the sun. As sun is rotating its around its north-south axis, they produce some kind of a lawn sprinkler pattern moving radially away from the sun. And it takes basically a spiral form because of the rotation of the sun. And these particles can reach up to Pluto's orbit and beyond. And finally, they meet the interstellar medium. And as they propagate into the planet, interplanetary space, they interact with the geomagnetic fields and other planetary fields, and they have very many practical applications. The solar wind flares and CMEs, they strongly influence local space weather in vicinity of the Earth and the other planets and other solar system, even comets. So CMEs inject large quantity of mass and magnetic flux into heliosphere, causing geomagnetic storm when injected towards the Earth. And these events lead to disabling satellites and knock out electric power grids at high latitude. Flare-associated enhanced ultraviolet soft X-ray fluxes increase ionization of upper atmosphere, affecting radio communication, increasing the drag and orbital decay of low orbiting satellites. Sometimes, in fact, the satellites lose their orbits and they fall into the Earth's atmosphere and then finally burn out. Hard X-ray and energetic particles can damage spacecraft and space instruments. Their radiation risk poses major concern for manned mission. Solar energetic particles lead to aurorae in Earth's polar and high latitude regions. Radio emission and decimetric wavelengths disturb the operation of GPS, radars, and other devices. There are lots of things happen which make space weather a very important project, and forecasting of space weather directly relates to the observation of the sun at various wavelengths. So this is showing the aurora which is resulting because of the particles, solar wind particles, which are trapped into the polar regions of the Earth, and they produce such bright emissions in the atmosphere of the Earth, around 200 kilometers above from the ground, and one can also see it from space as in ultraviolet as an oval ring. So this shows basically the aurora shows a sun and earth connection and the space importance of space weather. So we have discussed that the outer layers of the sun cannot be observed from the ground because it emits mostly in ultraviolet, extreme ultraviolet, and X-rays which do not reach the ground. So as a result of that, one needs to go to space. And as I said, that Skylab started the space era, observing the sun, and the coronal holes were discovered. And after that, several instruments have been sent by Japan and European Space Agency and NASA. And uh, now, of course, we are talking so much after Chandrayaan, we are talking about AdityaL1. But before our Aditya, several other satellites like SOHO and SDO, Solar Dynamics Observatory, observatories have been observing the sun. So we are actually a little late entrant, but Aditya is going to be the first dedicated Indian solar observatory. It has certain specific objectives, some kind of uniqueness. So essentially, this Aditya was kind of idea was brought somewhere in year 2000, and somewhere in 2003, Professor Yarrow suggested that why not send it to the Lagrangian L1 point. The Lagrangian L points basically are positions in space where small objects tend to stay if they are put there. So there are several Lagrangian points for a Sun and Earth system. This is a two-body problem where certain stable points have been actually not very stable. There are certain halo orbits around these where if you put a object, the gravity between the Sun and Earth is mostly cancelled, and one has to put very little energy for the spacecraft to keep it in a halo orbit in such locations. So L1 is a Lagrangian one point which is between the Earth and the Sun, and if you put a satellite at this place, then it is able to observe the sun continuously. L2 has the importance. This is farther away from the sun and Earth. This is Lagrangian L2 point where the telescope, like Webb telescope, has been put recently, some years back, for observing the the fainter objects, which is actually basically at the night side of the Earth. You can see here, so the sun doesn't trouble you. The bright emission of the sun doesn't affect it from observing the faint objects. But this is L1 point is roughly 1.5 million kilometers away from the Earth toward the sun, at which one can put a telescope like SOHO was earlier launched at this point. Now Aditya will be going there. So this essentially tells you about the importance of L1. And there are other points. If you can put at L4 and L5, then one can have kind of some kind of directional advantages also of observing the sun from various angles, not from just one angle, but from here and here. It can give a stereoscopic view of solar activity. So some future things which we discuss later on. I think I have almost taken roughly 1 hour and slightly more, but I'll just finish in couple of slides after talking about this. Aditya L1 trajectory to Lagrangian L1 location. This mission will be launched by ISRO PSLV rocket from Satish Dhawan Space Center, Sriharikota, expected to be launched in the last week of August, or if it is slightly delayed, probably in the first week of September 2023. And initially, the spacecraft will be placed in a low Earth orbit, it's like that. And then subsequently, the orbit will be made more elliptical, like this one. And then a spacecraft will be launched toward the Lagrangian point L1 by using onboard propulsion. As the spacecraft travels towards L1, it will exit the Earth's gravitational sphere of influence, SOI. Then the cruise phase will start, and the spacecraft will be injected into a large halo orbit around the L1 point. It is like what it was done by SOHO earlier, the NASA spacecraft. The total travel time for launch of Aditya to L1 will take roughly 4 months to take. Like for our moon, we know that it has taken slightly more than a month. It is much more than 1.5 million kilometer is nearly 5 times the distance of the Earth and the moon. So this is going to take a little longer to achieve this particular location. There are several instruments which have been developed by various scientists, solar scientists of India, located in various institutions, and they have collaborated with various centers of ISRO. So there is a visible emission line coronagraph. I talked about the visible emission lines of iron, yellow, red, and green. So they are basically optical lines which we can also observe from the ground during solar eclipses. But this will have a coronagraph in space in Aditya, and it will observe the solar corona and dynamics of coronal mass ejections. This was developed by Indian Institute of Astrophysics in Bangalore. Solar ultraviolet imaging telescope or suite payload images of solar photosphere and chromosphere in near ultraviolet. Again, ultraviolet doesn't come to the ground. The idea is to make images and also obtain the solar irradiance variation in near ultraviolet. This was developed by scientists based in Inter University Center for Astronomy, Astrophysics in Pune, IUCA. And then Aditya solar wind particle experiment. I talked about the solar wind. The sun produces a continuous stream of solar wind particles. So these will be measured using aspects. And there is a plasma analyzer package for Aditya called PAPA. And these were developed by PRL Ahmedabad. And PAPA is more or less, developed a Space Physics Laboratory, SPL, at VSSC, Thiruvananthapuram. So they are going to study the solar wind properties at the location of L1 in situ observations. Then SOLEX is solar low energy X-ray spectrometer, and then the other one is high energy L1 orbiting X-ray spectrograph. Also, you can call it Helios. There's one here, not I. So HEL1OS, Helios. Study the X-ray flares from the sun over a wide range of X-ray energy range. SOLEX is developed by U.R. Rao's Satellite Center, Bangalore, named after Professor U.R. Rao after his death. Helios is developed by PRL and USO scientists, and also U.R. Rao's Satellite Center. And there is a magnetometer to measure the magnetic field, in situ magnetic field of the interplanetary magnetic field at L1 point, which was developed by U.R. Rao Space Center and Laboratory for Electro-Optical System, Bangalore. So one can see that Aditya has a collaborative involvement of a large number of institutions, Indian institutions, who have contributed various instruments for various types of science goals. So let us come back, after we hope that Aditya will be launched successfully, and this will give a huge amount of information about the sun. So in the future also, we expect that only certain limited set of instruments are basically sent on board a spacecraft due to the restrictions of mass, power, and volume. So not everything which people want to do can be done in one satellite. So one requires the measurements from L1 using other instruments for measuring multi-directional and from other Lagrangian points. Also, the polar regions of the sun are not well studied due to technological. Ulysses has been one exception, but otherwise not much has been done about the polar regions of the sun, because one has to go above the equatorial plane, which requires huge amount of technological challenges, energies, and so on. And this is very important to study that because the solar polar dynamics and magnetic fields are believed to play a very important role in understanding the solar cycle. And apart from that, the polarization measurement of solar radiation. Different wavelengths are required to understand process occurring in and around the sun. So a lot of challenges are there which remain even after AdityaL1, although Aditya will be addressing huge number of challenges, and it will help us understand several uh, important problems, including the solar heating, the coronal heating problem. As I said that corona is very hot, million-degree hot, and not much is understood why it is so hot. So this actually just gives the summary of my talk, and essentially I would like to end here by saying the space-borne observations complemented by ground-based observations of the sun with increasing technological capabilities are required to further enhance our understanding of various scientific problems. So yeah, I think this is the last. There is just some kind of references which people can go through for more details, and I think I'll stop here. I taken quite some time, but I don't know whether there is some time for questions. So I leave it to now Anjan to take over from me from
No,
here.
sir, we are not giving permit to leave, sir, because lots of questions, sir. There is a flood of question. I think
I
you
see.
need another session if you go through this, and very critical. Some question is also there.
Okay.
If you allow me, to I would like to share with you.
Sure, sure. Yeah, please.
Sir, first preliminary, I have categorized all the question one by one, from very simple, which has been asked by some students and some veteran science communicator, and scientists also kept some questions, so critical questions. So from students to scientists, I am just categorize the question and
Okay.
just putting to you, sir. First of all, one have been asking that student, very interesting student, that nowadays India and other countries are moving forward to observe, to analyze sun. So whether the sun is a model, or there is in universe there is some more modified form of stars.
Yeah, actually, it's very difficult to cover everything. Sun is, as I mentioned, that sun is very important for us because one can uh, resolve the structures due to the proximity from us. But it is a modest star, average star. There is nothing special. There are stars which we see in the night time, you know, thousands and thousands of stars, which are our local surroundings. We see up to few hundred light years around us, and it shows, a variety of stars which are roughly 1/10 of the size of the sun to hundreds of times larger than the sun. So there are very large stars, there are very small stars, and sun is, if you consider the distribution of stars uh, it, as with respect to their temperature, spectral class, and so on, sun is a middle level star, mid level or very small modest star. But only thing is that by observing the sun, understanding the sun, we can also infer about other stars which are similar to the sun. There are the larger and the stars which are bigger, they have shorter time scales to live. I mean, our sun is already around 5 billion years old, and it is expected to last around another 10 billion years or so, because it is not consuming its uh, total mass so rapidly. The larger stars, they consume their material very rapidly in the core, for example, conversion from hydrogen to helium, then it goes to lithium and so on. And finally, they blast off in the form of nova and supernova, depending on their mass. And finally, they can produce a neutron star, a black hole, depending on their mass. If it is roughly 4 times the size of the sun, then it will end up as a black, black hole. So you have a variety of stars, but still sun is providing lots of information to understand the structure and the internal structure dynamics of the solar-like stars. So I hope I answered what he asked me.
Sir, another question from Anil Thanbi. I think he is a great science communicator also. So, sir has put on question. Several questions is there. Just first question is the sun rotating or it is twisting?
Sun is rotating, as we can infer from the motion of sunspots on the photosphere. On a daily basis, we can see, when the sun is a little active, we'll see sunspots at different latitudes of the sun. I mean, the equatorial region rotates faster, and as you go towards the pole, north and south pole, it takes longer. If you take a sunspot closer to the equator, it takes roughly 28 days to go through the complete rotation. But as you go towards the higher latitude, it takes around 30 to 32 days. So it is differentially rotating. And as a result of that, it leads to the twisting of magnetic field structure. If you consider a magnetic field line from connecting North Pole to the South Pole, a bipolar structure, magnetic field structure, as a result of this differential rotation, the magnetic field rope, which is joining North to South Pole, they will start twisting, and then finally they get so much twisted that they break and produce sunspots. So in a way, the twisting is occurring because of the differential rotation of the sun. It rotates differentially because it is not a solid body. Unlike Earth rotates like a solid body because we know that Earth is, except for the molten core, the Earth is all solid. So whether you are in Udaipur or you are in Trivandrum, we rotate, take 24 hours to rotate around this axis. But in the sun, it is not so. Yeah.
Sir, one student asked that why this Udaipur Solar Observatory has been situated on a lake, on an island. Is there any beneficial effect? Why this has been chosen?
Yeah,
Yes, compared with Sriharikota, he has been compared with Sriharikota and all the things. I am just commenting this. Main thing is there.
Sriharikota has been selected due to special consideration of launching of rockets. It takes advantage of the Earth's rotation, and it launched towards the Bay of Bengal, and there is a benefit of the rotation of the Earth there towards the equator, and also the benefit of the seas there, that in case something happens, it will fall on the. I mean, if you remember, our ISRO has gone through many such problems in the beginning when Professor Rao was the chairman. Lots of such thing happened that there were some explosions in our early attempts, and then fortunately it did not fall on the ground, affecting the population. It goes over the Indian Ocean and so on, and finally it is launched into the space. While for observatory, I think I showed one slide for the site survey. That for any astronomical site, you have to have some kind of site survey. For solar observation, you require some consideration. For nighttime, you require some other consideration. You have to be nighttime, you have to be away from light pollution areas. So like in Ladakh, you have one such place. And also in IIA in Kavalur was operating. Of course, now it is having a lot of light pollution. But normally people go to mountain sites like in Infrared Observatory, Mount Abu. It has advantages of height where you have dust-free environment. You are above the inversion layer of the Earth's atmosphere, so clouds are less annoying. For daytime, you require a place which has high duty cycle where you can observe the sun without clouds and without disturbances in the daytime for a larger number of days in a year. And we were looking for a lakeside because it has been shown by historical surveys by John Evershed and similar people in solar astrophysics says that if you are surrounded by a large body of water, the turbulence of air due to the heat of the sun is reduced, because as you see that during summers when you're walking on the road, you'll see some kind of mirage like thing, because of the heating of the ground, and the ground has the air which gets turbulent due to the heating of the ground, and that turbulence produces the convection currents in the air above that ground, and as a result of that you'll see this twinkling. That twinkling of the stars also you see as a result of this atmospheric heating. When you see stars closer to the horizon, you'll see that the stars, point objects, are twinkling, isn't it? So we say twinkle, twinkle, little star. So similarly, for the sun, this twinkling effect, which is produced due to the ground heating, it creates a problem in the resolution of fine structures of the solar photosphere and chromosphere. So when you are surrounded by the cooling surface of water around your telescope site, the turbulence of the air is cut down because the water top is heated, and then it will transmit heat faster to the lower layers of water then as compared to giving it to the atmosphere. So you will have, as a result of that, you will have actually lower convection, lower turbulence in the air, and as a result of that, the telescope, solar telescope, will be able to see very fine features on the sun. So this has been proven true, and the first such lakeside telescope was built in Big Bear, California, and second one was done at Udaipur by Dr. Arvind Bhatnagar, who was also one of the founder members of Californian Big Bear Sunspot, Big Bear Solar Telescope. He returned back to India and established that this solar observatory in Udaipur in a very similar environment after the California experiment. And third such telescope was built by Chinese near, Huairu in China. So there are such things, and also in Canary Island, which is surrounded by a large body of ocean water, solar telescope is located, and so on. So this is the advantage to have a solar telescope within a large body of water, and that's why Udaipur site was chosen, where monsoon effect is also less compared to the rest of India. If you go to Assam, you will have huge amount of rainfall, and you will not be able to see the sun for a large number of periods. But at Udaipur, this is one advantage, that we can see the sun for a larger number of time in 1 year, and also the cloud formation is lesser as compared to other. But of course, nowadays it has been happening in Udaipur as well, that the duty cycle has reduced as compared to the earlier time. So I hope I answered his question. Yeah. So,
Sir, next question. Sir, as per the hypothesis, this student asking that this, as per the hypothesis, Earth formed from the sun by through the AdityaL1 mission. Could we confirm that one, that Earth has been formed from the sun?
no. I think this is some kind of a misnomer, I feel. Basically, when sun collapsed, and the proto-sun basically ended into the sun, that basically created the central object, not directly related to the formation of the planets. Of course, planetary formation is a completely different thing. As it is collapsing, essentially people thought that some kind of a solar disk would form, and that will cool down, and finally it will be collapsing into different planets. So that is a different thing, but one cannot say. One can of course say that a huge molecular cloud was probably collapsing, and the central part collapsed into the sun, and as a result of the rotation of the protosun, the surrounding the central body uh, kind of disk was formed, which fragmented into planets. So you cannot say that the sun sent out some kind of a blob which created the Earth in that sense. So one has to actually see this entire thing from different perspective. Yeah, but I am not directly involved in this planetary formation, so I can only roughly tell you about this. Yeah.
Sir,
Yeah,
another question: why sunspots increase and decrease in each solar cycle?
yeah, the number of sunspots increase. Of course, they are form they form in groups and also isolated sunspots during different phases. Uh, and solar cycle, as I was talking, that if you start with a magnetic field line joining north and south poles of the sun, as a result of the differential rotation, the magnetic field lines get twisted, and this twisting leads to the breaking of magnetic field from the subphotospheric layers from from somewhere closer to the convection zone, from the bottom of the convection zone. The magnetic field actually burst out into the photosphere, and it depending on the overall structure and the dynamics of these magnetic fields as they are coming above, they will break out at different places, mostly close to the equatorial belt. The sunspots, they mostly form within plus minus 40 degree north or south, so plus 40 degree is north and minus 40 is south. So within this latitude, they will be forming at different times at different sizes. But as actually the twisting increases, the ascending phase and descending phase will depend on the progress of this solar cycle. This basically is explained in terms of the dynamo model, Babcock dynamo model, which talks about stretching of magnetic field, breaking into from toroidal to colloidal magnetic field structures, and they will show up as sunspots at different places. And finally, they will
Sir,
cancel
one
out.
another.
Yeah.
Sir, just two more questions, sir. One is
Yeah.
very much interesting, and another question, sir, that is, uh, first of all, the formation of in COSPAR has been done. Is it the recommendation of INSCORPAR that PRL has been structured? Someone asked, sir.
I didn't understand the question. In fact, PRL was born much before INCOSPAR. INCOSPAR came into existence only in 1962. PRL was founded by Vikram Sarabhai in 1947. So basically, the PRL is the mother institution, much older. And in fact, as I said, that it started with atmospheric and magnetic field, Earth's magnetic field, observations, atmospheric physics. So essentially, in the beginning, the small rockets were fired to understand the atmospheric dynamics, and also it very close to the equatorial region. These rockets they gave the discovery of electrojets, which was discovered by PRL scientists in the early phases. Much later, when the satellites were launched by Soviet Union in 1957, the Sputnik 1 was launched. So around that time, the International Geomagnetic Year was there, when the modern day maximum solar maximum had occurred, and the solar observation at that time and its effect on the geomagnetic field of the Earth was a very important topic. So at that time, it was realized by Professor Sarabhai that we should also do space science, and India should also begin its journey to the space. And that's why the idea of INCOSPAR was Indian Committee for Space Research was mooted by him, and he convinced Pandit Jawaharlal Nehru to support INCOSPAR. And this INCOSPAR finally turned into ISRO later on in 66, 67 onwards. So it has, during the time of Sarabhai, a network of many facilities were created, including Vikram Sarabhai Space Center, which was the TERLS, earlier TERLS under INCOSPAR, Tumba Equatorial Launching Center, where these rockets were routinely observed. So now, of course, the PRL will still continue atmospheric physics, which is a very important subject, but also has got a new division called planetary science division. You know, from the Mangalyaan onwards, that India has been dedicating to the studies of other planets. So the recent programs in PRL have been formulated based on the recent interests of ISRO, like planetary sciences. So PRL has its own, background of space-based studies even before the birth of INCOSPAR.
Sir, just three question more, and out of three, one is, sir, how could one join the PRL? One student wants to know from you.
Okay, we in PRL we have various types of opportunities for students and also for teachers, college teachers, which are basically the summer student program, mostly for those students who
No, sir,
have.
Sir, sir,
Yeah.
sir, he wants to join as a scientist, as a researcher.
Yes.
How could
Yeah.
as a career building?
Yeah, I think this career building is a long drawn process. Starting from your college, you have to have deep interest in sciences. And of course, PRL involved in a variety of subjects. You know, apart from space research, it has theoretical physics and as you see, geophysics and so on. So essentially, you have to have background in science, and as a research scholar, you enter, which is early phase of a scientist. You enter as a research scholar after your masters, or as an engineer after your BTech or MTech. So normally during summer months, PRL and also other institutions like Indian Institute of Astrophysics, Tata Institute of Fundamental Research, there are several national institutions which take students for PhD. So one has to have a good background in science with a good career in master degree, and then you apply for the entry as a research scholar. The interviews are held, and normally you have to have some kind of written examination and interviews, and also if you have a net or get qualified qualifications, then also one can apply. And of course, the written test is waived off for such people. They are also directly taken for interviews, oral interviews. And based on that, a good number of students. Earlier, PRL used to take 5 to 10 students per year, but nowadays PRL takes a larger number, around 40 or so, or sometimes even more, to cater to various divisions of PRL. So one can enter there, and then if you have a good research career through your PhD, then you do your postdoctoral in India, in PRL or other institution, and then you can also go abroad to continue your postdoctoral fellowships. And then, if things take you to different trajectories, you can be a scientist in other countries like in US or Europe, or come back to India and join one of the institutions like PRL or TF, as a faculty member. So the faculty member for PRL, which are called as the regular scientists, they can come also after doing several years of postdocs in other countries, having good experience. And again, they have to go through certain exam, kind of qualifier examinations. So these are quite a time drawn processes, which make you a full-fledged scientist. For example, I did my PhD, MSc from Raipur University, Pandit Ravi Shankar University, and then I joined PRL after written and interviews, oral interviews, in 1975. And then in 1981, I completed my PhD in astrophysics. And then I shifted to plasma physics, numerical simulations, and so on during my postdoctoral period, 2 years postdoctoral in PRL. Then I joined as a faculty member in Udaipur Solar Observatory. So it is MSc plus really something like 8 years that I landed here. Sometimes it takes longer, sometimes it can be shorter. So that is the process, I think. And then, of course, as you evolve, your interest will evolve, you'll do different types of research as you grow. You can change your subjects, you can continue depending on the new challenging areas, you can also change. So that is how a scientist will continue his career in science. Yeah.
And sir, before the last question, one more question, sir. One student asked that the uh, the Chandrayaan and Mangalyaan uh, got its trajectory through the using the orbits around the Earth and gravitational force of Earth. So likewise, AdityaL1 also going in such way or directly to L1
No,
point.
I showed the trajectory of Aditya. This is also going through certain, orbiting around the Earth, because PSLV and even GSLV, as you see, is not powerful enough to directly take you out of Earth's gravitational field. So even this Chandrayaan was made to go through this kind of swing shot trajectories around the Earth, picking up energy from the Earth's rotation, and then finally going over after 5 such elliptical, orbits around the Earth. It picked up enough energy to leave. As it increased the distance from the Earth, the gravity reduced, and then finally it could leave out the Earth's gravity and then entered into the lunar orbits. Similarly, Aditya is also going to do the same thing, because it will be launched by PSLV, which has lower energy compared to GSLV. So this is also going to take several orbitings around the Earth, and then it will go over to the Lagrangian point and then switch over to halo orbit. Mangalyaan also had done the same thing. So most of, like recently, Luna 25 has been sent by Soviet Rus, and their rocket was more powerful, much more powerful. So it has left much later than our Chandrayaan 3, but it is expected to land before Chandrayaan 3, does the landing there. So because they could, they have a very powerful rockets, launch vehicles. Rockets are basically launch vehicles. Similarly, NASA has those which could directly break out of the Earth's gravitational field and go directly, making it much shorter, like a week's travel time from Earth to the Moon. But we have taken roughly over a month to reach the Moon now. Right now, we are very close to the Moon, roughly 150 kilometers above the Moon. So AdityaL1 also is going to follow the same process, same advantage. So that makes it lower cost. When we talk about lower cost, Basically, it comes because of the lower cost of the launching vehicle. But we are still managing to reach by all these complicated maneuvers. We can reach our goal, like we reached Mangal planet, Mars. We reached our Chandrayaan 1, Chandrayaan 2, and now Chandrayaan 3 also reached the moon. So we have been successful in our very intelligent process, through which we have done. Of course, it has taken a little longer time, but our people have made it possible by this ingenious method. So L1 also, journey to L1 also will be on similar footing. Yeah, I think very nice that people have been asking questions, and I, I'm I'm not
Yes,
so
sir.
sure how
Yes,
many
sir.
people
Sir,
are attending, but maybe now people have been
sir,
getting
sir,
impatient. Yeah.
sir. If we calculate our whole program, sir, for last 2 3 from onwards 12 August we are conducting this mission Chandrayaan, uh, India International Saravai Student Scientist Award lecture with scientists and interaction with scientists. But your lecture is too much uh, appreciated by the viewers all over the country, and so many questioners there is flood. So interest about Aditya L1 and about you is maximum, sir, in its height and its peak. So thank you, sir. Just last question. One student ironically asked, what choose any one which will land on the moon first, Luna 25 or Chandrayaan 3? He asked
Yeah,
you.
yeah,
basically,
yeah. I think
basically, as far
I,
it is
I
concerned with the technology, as far
yeah.
it is
No, I
concerned with
mean,
the
as
technology, as you said, innovation and high profile, maintaining the trajectory. I think our scientist has done a great thing. Even Luna 25 lands on the surface of the South Pole first. Then also, it is going directly, not in such a innovative way, using all these three, the 4 5 trajectories, orbits, and
yeah,
using
and all
gravity of
around.
in Earth and other things. So he wants from you that which one you will choose, Luna 25 or Chandrayaan 3?
Yeah, I think as an Indian, of course, I would like our Chandrayaan, lander Vikram rover to be the first one, so that we can claim that we were the first one to land there at the South Pole. But when ISRO sent out this mission, that time this Luna 25 was not there in horizon. We did not know about that, and this came as a surprise to many of us that they planned. And
Correct, sir.
now, of course, since their rocket was more powerful, and they have already tested such rockets earlier, so they could actually make a faster exit from the Earth's gravity. So they also, I think it will be like, the in science we always have such open competitions, and we really wish them luck, and also we wish our ISRO scientists the luck. But as I said, that as an Indian, I will be very glad if we can make it first there, and this time successfully land there. Of course, our Chandrayaan 2 was also successful to a large extent, that even now it is orbiting the moon, and it is still there. And although the lander landed there, but it had made a hard impact, but it still made the contact with the lunar surface. Unfortunately, it crashed due to the little confusion there in the calculations, as the chairman had explained earlier. So anyway, I think as our students there, I will also be very, very happy. Let us wait for this week, and see what happens. And I'll wish our ISRO the great success this time round, and wish all our Indian citizens very happy times, within this next week or so. Thank you for such curious audience. And if you have any other question, you can always forward me on my uh, email ID. There is, I will be
Sure,
happy
sir. Sure, sir.
yeah, to answer later on as well. Yeah. So I think thanks you, Anjan, again. Thank you so much again for inviting me. And I had good time interacting with you and also with your audience. Thanks a lot. Yeah.
Thank you, sir. Thank you being with us, and we hope in future also you will give your blessings to us and with your cooperation and words of wisdoms. So, sir, for this, I would like once again, I with a congratulation, I would like to conclude you here, sir, and
Thanks.
for our audience, you can revisit this video to our YouTube channel. We have given the channel address here also, so you can, and if you have any queries, if you have any questions, comments, you can comment there in YouTube channel, and we will take it. Please mention your name and email, and will arrange some certificate also. We will participate in this complete session of Mission Chandrayaan lectures by the scientist of legendary scientist of India. We'll convert that one next month and due time. So you just mention your name and email in the YouTube channel comment box, and accordingly we'll sort it out and submit this certificate to all of you for your kind presence, for your kind gracious presence in this program, because viewers, all our students, teachers and science communicators are the main target audience of this events, and they are the main inspiration of our program also. And our scientists, as usual, they are also happy in communicating with all. With these words, I would like to conclude here. Thank you, Ashok sir, once again for
Thank,
being with us. We
thank,
need your continuous support, continuous blessings for in this moment. To our mission is making scientists for future. Thank you, sir.
thank you. So bye for now. I leave
Thank
now. Thank you so much, Anjan. Yeah.
So once again, we are requesting to subscribe our channel, YouTube oblique user oblique Anjan writer, where it's all are available. And with these words from my side, myself Anjan Banik is concluding here. And please subscribe our channel and support this mission, uh, mission of making scientists for future. हमारी इस आयोजन को आपकी हार्दिक सहायता चाहिए, और इस सहायता के लिए ज़रूर आप सब्सक्राइब करें हमारी यूट्यूब चैनल को, youtube.com/user/Anjan writer. Please do subscribe our channel. आपकी एक सब्सक्रिप्शन, आपकी एक लाइक, आपकी एक कमेंट, ये आपकी एक शेयरिंग इस चैनल को, इस मुहिम को आगे ले जा सकते हो। देश को आगे बढ़ाने के लिए, देश की नई भावी पीढ़ी को वैज्ञानिक बनाने की जो मुहिम है, इस मंच से मैं और मेरे साथी गण, जो कि नेशनल काउंसिल ऑफ रिसर्चर टीचर साइंटिस्ट इंडिया और नेशनल काउंसिल ऑफ स्टूडेंट साइंटिस्ट इंडिया के साथ जुड़े हुए हैं, इन सभी को आपकी बहुत ज़रूरत है. So subscribe this one, and also I would like to invite all the students to participate in next 5th year India International Sarabhai Student Scientist Award 2024 program through registering and answering the questions which is available on Google form e-quiz, and the link has been given in the scroll bar also, which will open from 1st January 2024 and will continue for every Sunday in between the period of till 28th February National Science Day. With these words, I am concluding here. Namaste. Tomorrow we will come back with another scientist accordingly. So be happy. Jai Vigyan, Jai Hind.